These are things which we covered in the last class. This is one of the most widely used circuit compared to other bias circuit. It is started with fixed bias circuit, emitter bias circuit, and this is going to be the third one, which is voltage divider bias circuit. As mentioned here, this is voltage divider bias circuit. That's about the last class. So today's class will give you some of the advantages of this bias circuit. Few advantages. The main advantages of this circuit is this voltage divider bias circuit uses only one power supply. One that is particularly DC power supply. First advantage. And coming to the second advantage, the advantage is for us because if you look at the same thing for emitter bias circuit, there we have a ratio of RB by RE. To maintain the ratio, we have two separate power supplies. Okay. But here the advantage is this needs only one DC power supply. Because here this is going to be a DC power supply, colorful power supply, DC. And apart from this, what else we have? If you look at operating point here, operating point is independent of the transistor gain, which is going to be V. Is it true? Other understood? But second point, what I am trying to say? Operating point is independent of transistor gain beta. Look at this expression for ICQ and because in this we don't have beta term, right? Look at VCQ term, we don't have beta term. But look at ICQ term there is some beta, right? Can we make it ICQ independent of beta? Just give some attention for the equation. Rewrite the equation so that we can easily get through that. What is the equation for ICQ? ICQ is equal to beta times numerator VCC minus V Thevenin. What about denominator? 1 plus beta times RE plus R Thevenin. Is it right? This is the equation for ICQ. Anyway, I am ignoring here VCQ because that the VCQ operating point does not depend upon beta. That's not our intention. We want to justify this answer. Operating point, how it is going to be independent of beta? Look at this. Can we make somehow this equation independent of beta? ICQ, we should not depend upon the beta. Is that it? Look at this. When you compare this one, look at denominator particularly. R Thevenin and as well as 1 plus beta times RE. When you look at this one here, we can make some approximations here so that the operating point becomes independent of beta. How the approximation is made is here. R Thevenin, you look at mathematical expression, it is a parallel combination of RB1 and as well as RB2. Right? So this quantity is going to be very small. Parallel combination. Now the serial combination will be larger. Parallel combination will be a very small quantity. So this term can be neglected because this is going to be small compared with this term, right? And look at in this term also here, 1 plus beta. Beta is going to be in terms of 100, 200 like that. Okay. And you compare with 1. Say assume that beta is 200 and this is 1. 1 plus 200. 200 becomes. So can we ignore 1 there? So to simplify this equation. So what will be the approximated equation if you look at it? Beta will be beta as it is. Look at denominator. This is neglected. Left out with only beta times RE, beta times RE. What about numerator? VCC minus V Thevenin. This beta cancel with this beta. This is approximately equal to VCC minus V Thevenin divided by. Is it right? That means beta variation does not affect this result currently. That's what we showed so far. Understood this thing? So that's going to be the second advantage from the voltage divider bias configuration. The first advantage is only 1 DC power supply this configuration means. Second advantage is operating point is independent of transistor gain beta. And third advantage is going to be is one of the most widely used configuration among various configuration. This is most widely used configuration. As you can see today, every CMOS C amplifier circuit contains this voltage divider. That's why it's one of the most widely used configuration compared to other kind of configuration. The last advantage of this is this provides better stability. Okay. Better stability. See, we have come to this particular bias because of the stability problem. Look at emitter bias circuit has got some stability problem. Temperature changes, transistor gain changes, operating point was used to change. But in this circuit, again, this provides better stability for variation of what? Variation of temperature as well as transistor gain, which is beta. Most of the transistor bias configurations, even when the temperature changes or the transistor gain changes, stability also used to change. But especially this type of configuration, even though the temperature varies to a larger extent, and even the transistor gain beta changes, this provides a very good stability. These are a few advantages of voltage divider bias circuit. Go through this. Any questions you have? And as you know, all these lectures will be recorded and that's going to be uploaded. I think 2 lectures are already available on YouTube. Okay, so anybody who was absent, they can download from YouTube and you can also listen. I think 1, 2, 3, 4, up to UJT emitter bias configuration is already uploaded. The only thing is you have to give in the Google search just a keyword about electronic circuits, the way to get a link so that you can download. I hope the download size is each lecture is around 700 to 800 MB. It's a bit difficult because of large resolutions they are going to capture and they are going to compress it and what is uploaded. So that's the thing. Any questions? Okay. So we have some modified version of this. The one drawback of this. Okay, which we have illustrated the same thing in the last class also. The one drawback here is because of this particular resistor, emitter resistor. As we know that this is the one resistor which provides negative feedback, right? Which we have started in the emitter bias. Because of emitter resistors, this circuit is going to introduce negative feedback to the circuit. That means whatever the current here flowing, the current normally which flows here is emitter current. Proportional to that, the input voltage is applied in opposite of this. That's why the current and as well as voltage is going to be both of this negative feedback it provides. But see that itself is a drawback for this. Reason is because of the negative feedback which is here, AC gain of the circuit will keep on increasing. Understand what I am trying to say? Because of negative feedback, what happens here? Who is going to introduce negative feedback? The resistor. If this is not there, means there is no negative feedback. Stability is a problem. Which was in the fixed bias, we don't have this. In the emitter bias, we have this. So stability is better. But here, stability is good. But at the same time, what is going to happen? The negative feedback, what it will do is the AC gain keeps on increasing. Understand it? What do you mean by gain? AC gain? The small voltage, whatever you apply here, I want to have a large voltage here. That's not happening because of gain here. That's whatever the voltage you apply here, the output is going to be very not larger, larger it is amplified, but only to smaller extent it has been amplified because of gain is reduced. Gain means it's a ratio of output voltage by input voltage. The AC gain keeps on reducing because of the negative feedback. So lots of people has done modification for this original circuit. That's what we illustrated in the last class also. what we need to do to overcome that AC gain is reduction of AC gain is just add capacitor here. This is called as bypass capacitor. This is bypass capacitor. Adding a capacitor, do you think here the DC analysis will change? These equations, ICQ and VCQ changes? Never, because the capacitor becomes a open circuit for DC analysis. So, since this capacitor is not considered in the DC analysis, this capacitor will not come into the picture for operating point. That means adding capacitor here will not disturb my operating point. So, it's advantageous. What about how this capacitor behaves for AC here and DC here? Whenever the AC signal comes here, this acts like a short circuit. This AC signal passes through this. But whenever the DC comes through this, when the DC goes through this will block it. Okay? That means the DC has to go through the emitter resistor. But AC can go through the capacitor here. Because for AC, this will act like a capacitor, act like a short circuit. But whenever DC comes here, DC cannot go like this. DC has to go through the emitter resistor. So that means this circuit provides better stabilization. Having this emitter resistor is advantage for us because I want to have better stability. At the same time, my gain should not decrease. To overcome this, the decrease in the gain, what we need to do is add some bypass capacitor. So this bypass capacitor improves the stability because this capacitor passes the AC signal and blocks the DC going through the capacitor. So that's going to be the modified version of this circuit. So with that, basic modifications, we will solve a few problems of which belongs to this voltage divider bias circuit, and we have left out with only one bias circuit, which is collector to base bias circuit. With that, we have covered almost common emitter configurations. So totally 4 bias circuits we have: fixed bias, emitter bias, voltage divider bias, and last one, which is the approach is collector to base bias. So with that coverage, we can start 2 to 3 topics are left in this unit. Very small unit topics. It's going to be thermal runaway, UJTs and tensors. Those things we can cover in a short time. You can take up this problem. Determine the values of resistors. Determine the values of resistors RC and RE. RC and RE for the circuit shown in figure below. For the circuit shown in figure below, given that you can take up R1 is equal to 5 kilo ohm, R2 is equal to 1 kilo ohm, beta is equal to 200, VB is equal to 0.7 volts, I1 is far greater than IB, VCQ is equal to 5 volts, and lastly ICQ is equal to 2 milliamp. Can take down the circuit. This is the circuit given. I1 is the current going through, this is not RB1 here, it is R1, and similarly here the given name is R2. This is 1 kilo ohm, R1 is 5 kilo ohm. Current flowing through the base of transistor is IB. Current which is flowing here is going to be A. And the voltage, everything is as usual. This is IC, which is current flowing in resistance, and this is R. Okay, you want to find out these two one is RC, other one is R, and VCC is given as 12 volts. Anybody can give me here what method here shows? Looking at the circuit and given conditions. Condition is I1 is look at this condition. You have to make use of that condition. The condition, whatever it is given here, reveals that this can be solved using approximate method. That's what condition you have to make use of this. Now you can see that you can apply KVL to the basic color section first and try to find out a general equation for this. Applying this is first. Applying KVL, Kirchhoff voltage law, to collector emitter group. We get, what do we get here? Minus VCC plus IC times RC is the drop across RC plus VCE plus current flowing in the emitter, which we label it as IE. So IE times RE is equal to C. Look at this. Any modifications which can be done for this equation? IE can be approximated to IC. So let me do it here. Since IC is approximated to IE, what will be this equation? Minus VCC plus IC RC plus VCE plus IC times RE, which is equal to C. Can you take out IC as a common factor? Send the rest of terms to other side. IC you take out as a common factor, RC plus RE, which is equal to VCC minus VCE. You just, because both are unknowns here, right? You can see that that's what we ought to find out for RC plus RC and RE. So what we do is rewrite this and send this to Dayananda. So what we will get it? RC plus RE, which is equal to VCC minus VCE divided by IC. Substitute this and find out right answer. VCC is given as 12 volts minus VCE 5 volts divided by IC, which is 2 milliampere. 2 into 10 power minus 3. Find out this and keep this as equation 1. We got 3.5 kilo. Yes, sir. What next? After this? See here, what you can do is let us call whatever the voltage here. Look at this is an approximate method problem. So let us call the voltage drop across this VB. Look at the expression of VB, which we already computed earlier. Yeah, VCC times here R2, not R2. It is R2 divided by R1. Use that and find out VB. Can write a condition here since what is the condition here? How you have migrated to this approximate method. Since so look at condition I1 is larger than IB base current. Okay, that means we use approximate method of analysis. From that, you know that expression for VB is given by VCC times R2 divided by R1 plus R2, substitute everything and calculate the value of VB. So is 12 volts into R2, which is given as 1 kilo ohm, is 10 power 3 divided by R1 plus R2. That means 1 into 10 power 3, that is R2 value. R1 is 5 into 10 power 3. The value 2 volts, right? Because here 5 plus 1 is 6. This 10 power 3 cancels with this. 6 is 2 volts. Okay, so that is VB is equal to 2 volts. So from this we will estimate VE. Drop plus RE. What is VE? Expression for VE. Okay. V is equal to VB minus VB. Using this, we find out V. What is VB? VB already estimated as 2 volts minus 0.7. This makes 1.3 volts. So this implies that V is 1.3 volts. Now using this, can we find out RE? What is RE? V by IC. That's right. So step 4. So RE, which is nothing but VE divided by IE, which is equal to VE divided by IC. So V is given as 1.3 volts divided by IC, which is 2 milliampere. Find out this value. RE value 0.65 kilo. So this implies that RE is 0.65 kilo. Now using this in equation number 1, we can easily obtain the value of RC. Using RE in equation 1, RC plus 0.65 into 10 power 3, which is equal to right hand side is 3.5 kilo ohm into 10 power 3. Simplify this and obtain value of RC. Subtract from this 2.85. That's right. 2.85 kilo. This is the value of RC. Any questions here? Next is one more problem on this voltage divider passive. Like I understood how to solve this type of problems. Today I am going to give you a couple of assignments which you need to submit in time. Okay. Exercise questions and as well as some exercise problems from the textbook. If you have textbook, how many you don't have this textbook? If you don't have the textbook, copy with the people who have the textbook questions and some review questions and as well as some problems which you need to solve. There is no compulsory to write an assignment. If you ask me, is it compulsory to write an assignment? No. But at the end, you want to consider for the final written assessment. Assignment plays an important role, right? If you are able to score out of out, then there is no choice in writing an assignment. Right? You can ignore the assignment. If you want to have some marks at the end, definitely without assignment, don't come to me for assignments. It is up to you now whether you want to write an assignment or ignore the assignments. But in my view, writing assignments is a good practice because I am going to ask a question from the review question from the textbook itself. You get practice, more practice, and it will be helpful for your main examination. Okay. At least even though if you score out of nothing wrong in this writing assignment. I am not going to give a 20 question or 30 question. few questions, these 10 questions. You have sufficient amount of time, 1 week time, so that you can try in your home. All are simple questions. Okay, any questions in this regard? So we'll go to the next problem. Should I do this? Okay. Take a business. Draw the DC equivalent circuit. Draw the DC equivalent circuit for the circuit shown in figure below. For the circuit shown in figure below. To start, calculate the quiescent value of emitter current. Calculate the quiescent value of emitter current. Emitter current, right? Using its collector current. Let's look at it. We can change that to collector current because it is unit. It's collector current. Maybe I have done wrong or in the textbook mistake. Using both approximate and accurate methods. Using both approximate and accurate methods. Full stop. What is the percentage error introduced? What is the percentage error introduced using the approximate method? Using the approximate method, given that transistor gain beta is equal to 165. Given that transistor gain beta is equal to 160. Circuit has small change. Okay, this is a circuit which is given. RB1 is 68 kilo, RB2 16 kilo, RC is 2.2 kilo, RE1 0.1 kilo, RE2 0.7 kilo. First one you can solve it. It is required here to draw the DC equivalent circuit of this. Go ahead. How to draw DC equivalent circuit of this circuit given. Yeah, remove capacitors and ignore AC sources, make it as 0. Okay, so left out is this circuit. Also see that if you remove capacitor here, this can be combined to single resistance. 0.1 plus 0.7 becomes 0.8 kilo. It can be combined to single resistance. You can write here. So let us write it here. Solution for this. First, let us draw DC equivalent circuit. So this is the DC equivalent circuit. The next step, what we need to do the next step. One is transistor gain beta is given as 165. You must here find out the quiescent points of the circuit in accurate method and approximate method. Try to find out the errors associated with them, right? That means estimate for the circuit ICQ, VCQ using accurate method. Same ICQ, VCQ using approximate method. Try to find out the difference between them. First, let us start with the accurate method. Second part of the problem is Q point estimation. Q point estimation using accurate method. So, how do you estimate the Q point using accurate method? For the first step in this, you have to replace this circuit with the Thevenin's equivalent circuit. For that, can you estimate V Thevenin, R Thevenin? About this. What is V Thevenin? VCC into RB2 divided by RB1 plus RB2. Substitute this and find out the value of V Thevenin. Thevenin is 18 nodes. VCC is given here. Take it as 18 nodes. 18 nodes times RB2. RB2 is given as 16 kilo. 16 into 10 power 3 divided by RB1 plus RB2. That is 68 into 10 power 3 plus 16 into 10 power 3. Work out this. Find out the value of V Thevenin. 3.43 volts. All of you got this answer? 3.43 volts. Similarly, find out the value of RThevenin. RThevenin is RT1 parallel with RT2 is RT1 into RT2 divided by RT1 plus RT2. RT1 is 68 into 10 power 3 into 16 into 10 power 3 divided by 68 into 10 power 3 plus 16 into 10 power 3. Yeah, 12.95 kilo. This implies that our Thevenin is 12.95 kilo. I will just need to draw the Thevenin's equivalent circuit of the DC equivalent circuit. Go ahead. Thevenin is equal to circuit. How can you estimate operating point? Apply KVL to the base emitter loop. Find out the base current expression. Then later on you can use transistor gain equation. This third one is okay. Let's apply KVL to the base emitter section. Apply KVL to base emitter section. You get? Apply KVL to the base emitter section of Thevenin's equivalent circuit. Minus VThevenin plus IB times RThevenin plus, don't forget the drop across base and emitter. VB plus VBE plus current flowing through RE, IERE, which is equal to C. Is substitution here? Yes, of course. I is equal to 1 plus beta times I. IV. So substitute okay, IE as 1 plus beta times IV in above equation. That is the case, what will be the solution? Minus VThevenin plus unless you can do one more solution. Here is beta is anyway given 165. 165 plus 1 is 166 times IV. Okay, that will be convenient, right? This IE as substitute as 166 times IV in the above equation. So that is the case, minus VThevenin plus IV times RThevenin plus VB plus instead of IE what we have is 166 IV times RE, which is equal to. Substitute everything and find out IV from that. VB is not given, you can take it as silicon transistor 0.7 volts. Okay, you can take it as VB as 0.7 volts. The value of IV, substitute everything. Minus VThevenin, continuation is here, you see, but it's minus Thevenin value is minus 3.43 plus IV times RThevenin 12.95 kilo plus VB 0.7 plus 166 IV and RE value you can see 0.8 kilo into 0.8 into 10 power 3. Simplify all these things and find out the value of IV. See here, but due to time limitations, I cannot give you access to solve all these problems. Go back to home and try to resolve all these problems for the class. Further, if you have any questions or doubts, you can come to me. Okay. Estimate IV value. Some of them may be faster and some of them. What's the value? 18.7 micron ampere. That's right answer. Those who haven't got this answer, just note down this answer and try to work out your home. Okay. Going this IV, what is next? Find out IC. IC is equal to beta times IV. That's going to be 4. We know that what the IC is equal to beta times IC, beta times IV. Beta is 165 times IV is 18.7 into 10 power minus 6. Find out IC. We're supposed to get IC as 3.08 milliampere. 3.08 milliampere. So far, any doubts here? Clear? Next is VC. See, all this is nothing but accurate method. For this we are working out, right? So next, find out VC. How do you find the VC? KVL you must apply to the correct elements. Okay, the out here. Let's call this is fifth. Apply Kirchhoff voltage law. Okay, to collector emitter loop of figure C. Okay. A third figure. Even here also, we said applying KVL to base emitter section of this is figure C. Confusion for this circuit. Just write a figure. Catch. Okay, so if you apply KVL to the electromagnetic loop of figure C, there is an equivalent circuit. What will be the answer? Minus VCC plus IC times RC plus VCE plus IE times RE, which is equal to C. Find out VC from this. So here also you get the approximation in place of IE, you can substitute as IC. So you can do it here. Since IE is approximately equal to IC, we get minus VCC plus IC times RC plus VCE plus in place of I we have IC times RE which is equal to C. Substitute everything and find out VCE value. Minus VCE, VCC is minus 18 plus IC is 3.08 milliampere. 3.08 into 10 power minus 3 into RC. Find 2.2 kilo ohm. 2.2 into 10 power 3 plus VCE which you want to estimate plus IC times RE. IC is again 3.08 into 10 power minus 3 into RE is 0.8. 0.8 into 10 power 3. Find out from this what is the value of VCE. $8.766. That's the correct. So right here, this implies that VCE is 8.76 volts. You can see I see VC values from the period method. 3.08 milliampere. VC is 8.76. So the complicated you can go for approximate. Same thing you want to estimate using approximate. Why? Just work out not efficient. You have not written anything. Which one? You have to make some arrangement there. Is that a problem? You cannot see, is that a big problem? Shall I arrange some projector for you here? So that's a big problem. Thinking that who told you to not to sit in first? Somebody told you to sit always in back. You have to make an arrangement. If you have any doubt, I can solve. If you cannot see far away, what can I do? here is a place. You can escape some bag. You can come and occupy this. Find a solution. You will get it. Simply sit at thinking that I cannot see anything means I will not help you. Okay, I cannot check all history here, right? Can I verify all 60 students what is there in your mind? Very difficult. Okay. I'm teaching this subject from past 8 to 10 years. Electronic systems. For these students will come and go. It is your duty to learn. If you have any